know that this is the era of the artificial intelligence. So to give the knowledge of a security, privacy and trustworthiness in the AI world, today we have a prominent speaker, Dr. Karthik Nandakumar with us. So it's my pleasure to welcome you, sir, on behalf of the SPS Gujarat chapter and team NetC. So welcome, sir.
Yeah, thank you.
So now, by giving a brief discussion about the speaker, after the introduction of the speaker, we'll start the session. So let me give a brief introduction of the speaker. The Karthik Nandakumar is an associate professor in the computer vision department at Mohamed bin Zayed University of Artificial Intelligence. Prior to joining MBZU AI, he was a research staff member at IBM Research Singapore and scientist at Institute of Infocom Research, A-Star Singapore. His primary research interest includes computer vision, machine learning, biometric recognition, applied cryptography, and blockchain. Specifically, he is interested in the research on deep learning algorithm for biometrics and video surveillance applications, as well as various security, privacy, and trust-related issues in the artificial intelligence. He has co-authored of 2 books titled as Introduction to Biometrics and Handbook of Multi-Biometric in the year of 2011 and 6 respectively. And both books was published by the Springer. Karthik Nandakumar has received the number of awards. He has received a Fitch H. Beach Outstanding Award in 2008. He has also received the Best Paper Award from the Patent Recognition Journal in 2005 and Best Scientific Paper Award in a Biometric Track at ICPR in 2008. And he is also he also received the IEEE Signal Processing Society Young Author Best Paper Award in 2010. He is a senior area editor of IEEE Transactions on Information Forensic and Security. He also received the 2019 Outstanding Editorial Board Member Award. Apart from this, he is also an associate editor for Elsevier Journal on pattern recognition and distinguished industry speaker for the IEEE Signal Processing Society. In the recent past, he has served as Vice President for Education in the IEEE Biometric Council and as an elected member of IEEE Signal Processing Society Technical Committee on Information Forensics and Security. He is also a senior member of the IEEE. So with this, I would like to hand over this session to Dr. Karthik Nandakumar. Sir, over to you.
Thank you for the kind introduction. Good evening to everyone. Hope I'm audible.
Yes, sir.
Yes.
Okay. Yeah, so hi everyone. So today my talk is going to be on security, privacy, and trustworthiness issues in the AI world. As mentioned in the introduction, I'm currently an associate professor in the computer vision department at Mohamed bin Zayed University of Artificial Intelligence. This is a new university which just started admitting students for the first batch in January 2021. So at MBZUI, I'm leading what is known as a Sprint AI lab, where we deal with mainly security, privacy, and trust issues in AI. So before I go into my presentation, I'd like to thank the IEEE Signal Processing Society, especially the SPS Gujarat chapter, for inviting me for this talk. And I'd also would like to give a brief introduction about my university. As I mentioned, this is a new university, which is kind of fully AI focused, and it's a research-based university. So there are no bachelor students here. It's only master's and PhD programs. And unlike other general universities, we don't offer things like computer science, electrical engineering, and so on. So we are specifically focused on 3 areas: computer vision, machine learning, and natural language processing. So all these things are related to the AI field. And the admissions for the fall semester is still open. So if anybody is interested, please feel free to contact me or the admissions office. So this university is like has been started mainly to focus on research. So it's fully funded. So whoever is admitted has a full scholarship and also a monthly stipend to go with that. Okay, so I'll start off with the outline of my talk today. So first I'll describe what is the motivation for my work, which is mainly vulnerabilities of machine learning systems. That's what motivates me to do this research work. And within this broad topic, I work on some key research problems. They include biometric presentation attack detection, robustness against adversarial attacks, against machine learning systems. Also, I work on fairness in machine learning and secure collaborative or federated learning and explainable AI. So these are some of the key topics which I work on. So I'll spend the first 10-15 minutes just highlighting these topics and then spend the rest of my presentation on one of the core topics which I am currently working on, which is machine learning on encrypted data. And finally, I will give a summary of my work. Okay, so when we talk about machine learning system, I'm sure all of you know how machine learning system works. Basically, there is a physical world. You have a sensor which kind of captures things in the physical world into a digital representation. And then once this digital representation is available, either in the form of images, speech files, text, or even just tabular data in many fields. So this digital representation is supplied to a training algorithm, which is called as a training data. You basically call it as a training data. And this is used to learn a machine learning model. And this model is stored somewhere within this whole ecosystem. And during what we call as the inference stage. So let's say you are given a new input and you want to make some prediction or inference about this input. You pass this input data to the inference algorithm. Basically, the stored model is applied on this inference on this input data to get the new inference or the prediction. So this is how a machine learning system works. But these kind of machine learning systems, if you consider the system as a whole, they are vulnerable to several kinds of attacks. For example, the first kind of attack is called as a physical spoof. So let's say you have a stop sign on the road and you have an autonomous vehicle or the autonomous car. It's basically trying to detect the stop sign using cameras. So basically you can make changes to this small minor changes to the stop sign so that it is never detected by the camera, or even if it is detected, it is interpreted as something else. So you can, physical spoofs actually refer to making changes in the physical world, which will fool your machine learning system. So another area where physical spoofs are very popular is in the area of biometrics. I'm sure all of you would have Aadhaar accounts and you use fingerprints very often. So as some of you may know, fingerprints, you can create what are called as dummy fingers or like spoof fingers. So basically, you can create fingers out of different kinds of materials like gelatin and so on, and use it to do an authentication instead of a real finger. So these are also examples of physical spoofs. And this particular kind of attack on a fingerprint system is called presentation attack. So physical spoofs is one possible vulnerability in a machine learning system. The second vulnerability is data poisoning, and this happens usually during the learning process. So when you create your training data, you kind of go and tamper with this data so that the learning algorithm learns something which is wrong, which is not supposed to learn, or learns it in a very incorrect way, so that during inference it will not work as expected. So that is basically known as a data poisoning attack. The third kind of attack is model tampering. So once you learn a model parameters, as I mentioned, it gets stored somewhere in the machine learning system to be reused during inference time. So somebody can go and tamper with this model parameters so that the inference does not work properly. So that's the third kind of attack. Then there is a bunch of attacks which can happen on the stored machine learning model itself. So this includes membership inference. So by membership inference, what we mean is, when you do this learning using this training data, this learning algorithm or the stored model actually contains some information about the training data. And this membership inference attack tries to find out what kind of data was used for training the system. So let's say I am given a stored model. I can do some queries on this stored model in order to find out whether, let's say, a particular person's data or a particular image has been used for training this model. Right? So that is called as the membership inference attack. The next one is known as model inversion. So by model inversion, what we mean is, so let's say given the stored model, it gets stored somewhere in the database, and if you are able to get access to the stored model, can I go back and reconstruct the whole data which was used to train this model? So that is known as model inversion. So basically, from the given all the parameters of the model, can you go back and reconstruct the data which was used to train? So in the membership inference, you are kind of querying the system and asking whether this particular training data was used or not. So it's a binary kind of system. Whereas in the model inversion, you're given the model and you can reconstruct the entire training data from the stored model. So that's the model inversion attack. Then we have what is known as the model extraction attack. So there are many companies today which provide machine learning as a service. Let's say Google has this Google Cloud platform where you can just upload your data. They will run this training on their own servers and then provide you with a machine learning model which works on your data. Well, this is called as machine learning as a service. And they also do prediction as a service, in the sense they already learn some model. So let's say you want to classify some X-ray image as whether there is a disease in this X-ray image or not, or some problem, let's say a fracture or something like that in a particular X-ray image. So Google already provides some services such as where you can actually upload your data and then it will give you a prediction whether this X-ray is okay or it has a disease or some kind of anomaly in it, right? So this is basically called as a machine learning as a service. You upload the data, you get your prediction output. And in this case, by just querying this model, actually you can learn many things about the model structure and the model parameters. That is basically called as a model extraction attack. So you just treat the model as a black box. You don't know what Google has, but just by sending queries, you submit some questions and then you get some answers. And based on these questions and answers, you can somehow guess what is there inside the stored model. So that basically represents the model extraction attack. Then we have one main kind of attack called as the adversarial samples. So today, many machine learning systems use what is known as the deep learning framework, which is essentially a neural network with many kind of layers. One of the problems with these deep networks is that they are easily fooled by what are known as these adversarial samples. So let's say I take an image and I make some small changes in this image, the inference on this image will completely change. So this kind of attack is known as adversarial attacks or adversarial samples. So finally, we have what is known as the breach of confidentiality, which means in the machine learning system, you have the training data and you have the input data. So you, by just looking at your learning algorithm or your inference algorithm, if you can find out like what was the training data used in the system or the input data supplied to the system, then it breaches the security of the data which is used in the system. And this leads to a lot of privacy issues. So these kind of attacks basically have three kind of problems or threats. So one is they attack the integrity of the system. By integrity, we mean whether the system is supposed to work as it is expected to do. So let's say you run a model to detect fraud in a banking transaction. By compromising its integrity, we can either get through the fraud model or like you can make things more difficult for regular transactions to go through. So that is basically playing around with the integrity of the system. The second one is availability. So availability means for genuine users. So somebody really wants to use the system, but by tampering with this, either the model or some kind of learning algorithm or inference algorithm, you make the system unavailable to these genuine users. And the third one is privacy and confidentiality. This is where you kind of give up access to your confidential data, which might be very sensitive. Let's say your financial data or health data might get compromised. So my overall research goal is to develop secure, privacy-preserving, and trustworthy machine learning algorithms and AI systems. So based on these, this is my main motivation for working on this research area. So now I'll just briefly describe some of the topics which I'm working on. As I mentioned earlier, I will present 5 different topics quickly before I focus on one particular topic. So first one I'm working on is what is known as biometric presentation attacks. So just as a quiz for all of you, like I have shown a few images here. Can anybody tell me which images are real from a live person and which ones are like photographs replayed to the system? Okay, so I think. Yeah. Are there any answers?
No.
I guess first row, third column is real.
First and last.
Yeah, actually, you'll be surprised to know that all of them are like fake images. In the sense that the first column is basically images where you print it on a paper and then replay it to the camera. The second column is basically you display the photo on an iPhone and then show it in front of the camera. The third one is you do the same thing using an iPad. And on the right, I show a lot of images. Actually, these images look very diverse, but actually all of them are from real person, live person. So this one is a very hard kind of problem because just by looking at the images, or this is same in the case of fingerprints also, just by looking at your fingerprint image, it's very difficult to say whether this comes from a live finger or a fake finger. Similarly, in the case of face, whether it comes from a live face or a some kind of a spoof, right? So,
Excuse me, sir.
yes.
If these are not real images, can we still say it's fake because they are just copy of a real image, right?
Sure, they are they kind of defeat the purpose or the whole purpose of the system, right? So let's say you have a face recognition system at the airport. If you can just show somebody else's photo and get through the security system, then it creates a big problem.
Yeah.
Right? So although they are copy, but then it no longer belongs to you, right? So you are no longer authenticating the person, but you are authenticating something the person is showing to the system. So which is a
they are
big
known
problem.
as fake image is only, or is there any another name for them?
It's called presentation attacks. That's the technical term given. So you can call them as fakes, you can call them as spoofs, but the ISO definition basically calls them as presentation attacks.
Okay.
Okay, so the problem here is it's very difficult to just by looking at the image or visually analyzing this image to say whether this is real or fake. But there are some minute variations in the texture which you can detect in order to say whether this is a real image or a fake image. The problem, one of the key challenges here is you can easily do it for one kind of fake image. So let's say I can easily develop a system which will detect a photograph being replayed, right? But then that same kind of model will not work well if you show the photo in an iPhone instead of a photo, instead of a printed photo. And similarly, if you show it with somebody, something else, let's say you play a video from the laptop, so it will be very difficult to detect that kind of a different kind of fake image. So that's where the problem of the core problem which we are trying to address here is domain generalization. So by domain generalization, what we mean is you can always develop a machine learning system that works well for the training data or data which is very similar to the training data. But once your data distribution changes a little bit, so instead of let's say printed photos, I use something else. So then it changes my data distribution a little bit. Then these machine learning algorithms fail to work. So how do you enable these machine learning systems to generalize well across all these different kinds of domains? So that is one of the key challenges which we are working on in biometric presentation attack detection. Okay, the second kind of attack is basically known as the adversarial attacks. So this one, as I mentioned, is very popular after the invent of these new deep learning algorithms, deep neural networks. So what people have found is that here I'm showing two types of attacks, right? So on the right side, you have basically three columns. The first column is the original image, right? And just by adding some kind of noise to this original image, which does not visually change the image. So the column on the right, the third column on the right is the modified image. So if you look at it visually, the one on the first column, the image of the school bus in the first column and the school bus in the third column look very similar to the human eye. What we have basically done is made some small modification by adding some noise to this image. But then for a machine learning system, all these images on the right column, right, the last column, they are all classified as ostrich. Although if you just provide the original image, they will give you the correct class. That first image is a school bus, second one is an animal, third one is a temple, and so on. But once you add this noise, the machine learning system gets fooled. So the noisy image or the adversarial image is misclassified into all these adversarial images get misclassified into the ostrich class, so which is very intriguing. So this is one type of attack. We can also do the other thing, right? So let's say there is a bunch of different kinds of objects which is shown on the left-hand side. So let's say some treasure, some flagpole, and some balloon and so on. So instead of adding different kinds of noise, I can come up with a noise pattern which can be added to these different images to make the system misclassify them. So for example, if I add this noise pattern in the middle to the flagpole, then the system misclassifies it as a Labrador. Or similarly, if I do something to the balloon, add the same noise image to the balloon, it gets misclassified as Labrador. So essentially, by adding the same noise pattern to different images, you can make the system to misclassify these images. Of course, this kind of attacks is a problem, but these are called as benign attacks, which means you're just trying to play around with the system. But there are some real-world applications where these kind of attacks are really dangerous. So, for example, let's say you have a stop sign and you have a computer vision system working in the autonomous vehicle, autonomous car. Basically, by modifying this image, you can change the stop sign into a yield sign. Although visually it still remains a stop sign, but the computer vision system detects this as a yield sign. So, and then this, as you can imagine, this can cause a big problem if you have self-driving cars on the road. Similarly, by wearing a few accessories, people have shown that like glasses or some kind of makeup, people have shown that we can easily fool a face recognition system. We can also change let's say, a gender recognition system. So if you have a face-based gender recognition system, just by adding some noise, you can change the gender class. If you have like a OCR system, by adding some small noise, you can just change the whole thing. So for example, here is the check for $158, and then you can change it to some big number just by modifying some few pixels around this near the numbers which you want to detect. Right. So essentially, these kind of attacks are malicious attacks. So again, the key problem here is how do you generalize well across these kind of attacks? People have come up with many methods that if you give me samples of original image and the attacked image, I can come up with a adversarial attack detection algorithm which will work for this specific class of attack. But then you cannot control the adversary in this case, right? You can come up with your own defense, but then the adversary can in turn come up with a different kind of attack which will fool the system. So how do you build a very generic kind of adversarial attack detection system which works across all the different kinds of attacks which the adversary can come up with? So that is one of the key challenges from the machine learning perspective. Okay, so the third problem which I'm working on is basically fairness of machine learning systems. So by nature, machine learning is some form of statistical discrimination. So because you're trying to distinguish one class from another, right? But then this kind of discrimination becomes objectionable when it places some group of users at an advantage and some other group of users at a disadvantage. So for example, many of the face recognition systems or face processing systems by leading companies in the world, they are biased against skin color. So they are all, one of the main problems there is the training, right? So most of these systems have been developed in Western countries. They work very well for Caucasian or white faces. The moment you apply the same system for, let's say, an Indian face or an African face, which is kind of a darker skin color, they will have much higher error rates compared to the error rates for the white people. Similarly, it also has a gender bias. So it works well for male, it doesn't work well for female. So basically, these kind of problems exist for face recognition systems. But this is also true in other kinds of applications. One of the main applications where this is a big problem is in the financial domain, especially if you are doing some automated credit scoring. Many of these automated credit scoring algorithms, which are used in banks and these other loan agencies, so they tend to be biased because historically loans have been given to the privileged class, and then they get all the and they get a lot of credit score and all that, right? Now, when you're trying to use this past data to learn a model, it actually learns the inherent bias in your original data. So what happens is when somebody from the unprivileged class comes in, then it gives you a low credit score, and basically you'll be denied a loan and so on. So this unwanted bias comes from two sources. One is the prejudice in the labels, which is basically there is some kind of human prejudice in many systems. So for example, in the natural language processing system, so people have found that whenever you type a word nurse, it is associated with a female. So it never considers the possibility of having a male nurse. So similarly, certain kinds of, so if you type a doctor, it will associate with a male, not a female. So these kind of inherent biases get inside the machine learning algorithm. And then how do you remove these biases is one of the main problems which we need to address. And the second issue is undersampling or oversampling, which I have already mentioned. So many of these, let's say, face recognition systems have been trained with male white faces. So it works only for that kind of people. To come up with people from the other class, then other ethnicity or other gender, then it doesn't work so well. And this is a real problem. Remember during the last year's protest in the US, when there was some racial issues during the Black Lives Matter protest. So what happened is all these big companies like Amazon, Microsoft, IBM, they all pull their face recognition systems from the market because many of these police departments are using these facial recognition systems, and people know that they work well for white people, but it doesn't work well for black people. And then it became, and there was a paper from MIT 2 years back, which actually showed that many of the systems are biased against certain classes of people. So because of this reason, there was a big hue and cry, and all these big companies, they pulled out their facial recognition systems from the market. They said they will no longer sell this facial recognition system until this issue can be addressed. Okay, so the fourth topic which I'm working on is basically known as the explainable AI. So the idea here is many of these machine learning systems, they try to learn some kind of mapping between the input and the output. So today you give an image, you give the training data, there's a learning process, and then when you give a new data, it just outputs that this is, let's say in this case, a cat or a dog. But then it has no idea about why this is a cat or a dog. In many of these practical world, real world examples, this is very important. So let's say you are doing a medical imaging system, you're developing an AI system or a machine learning system for processing medical images. If you just say that, oh, this person's, let's say, MRI or CT scan shows some cancer, right? It's not very useful to the doctor. So you need to say why the system considers this to be a cancerous image, right? So for example, in this case, if you say this is a cat, then why does the system say that this is a cat, think that it is a cat? Maybe it's because it has fur, it has whiskers and claws. But then today's machine learning system, they don't give you all these details. They just give you an output label. This is a cat and this is a dog. And many of these problems like the adversarial attacks, which I talked before, right? All these come up because these machine learning systems are so blind, and they are just, it's just like a horse running in one direction. They just want to improve the accuracy of a system. So you just blind the horse, it doesn't see what is there on the left or the right. It just moves towards increasing the accuracy. The problem with that approach is that the moment you change something in the image, then it does not know where to go. So that's why you get all these problems with adversarial attacks. So if you want to really get rid of this problem, then you need to have what is known as explainable machine learning models. So if you say this is a cat, image of a cat, you should be able to say, okay, why do you think this is a cat? Because it has fur, it has whiskers, it has claws, it has this shape of ears, and because of these reasons, I think this is a cat. So this is how human actually learns the model. And so one of the problems is, like, let's say you take a child. If you teach a child that, let's say this is a cat, you show the child a cat, the child will learn this immediately. So next time you show a different cat in a very different kind of scenario, still the child is able to recognize that this is a cat. But machine learning systems will not be able to do so. Today you show a cat, one particular type of cat, which is from an outdoor image, and then tomorrow you show a different cat which is captured indoors and so on, then the system will fail. The reason it fails to recognize this new plan, although it's the same cat, the reason it fails to recognize is because it's not looking at high level features or like global features, which are very important for understanding an image or understanding some kind of data. They just look at some local features which are kind of unexplainable, and then they try to make a prediction based on that. So that is why that is one of the major problems with today's machine learning systems. And there is an issue here. So for example, here I'm showing, let's say, a simple model, right? So here on the x-axis, you have the age of a person, and on the y-axis, you have the number of purchases made by the person. So let's say this is a shopping example, right? So, and this black dots actually show the real data points. And let's say I try to feed a very simple linear model to this data. So I can easily see that this model is not very accurate. So when the age is low, you have kind of what is known as lost profits, because you're trying to market something to very young people which they're never going to buy. And then similarly, you have wasted marketing on the right hand side. So basically this linear model is easily, but the problem is that the linear model is very easily explainable. So it's here we are saying this slope of this line is 0.8, which means for every unit increase in the age, the purchasing power increases by 0.8. Right? So you can easily explain this model. On the other hand, you have the model on the bottom, right? So this one actually fits the data very well. So it's able to accurately represent the data. So it has a very good accuracy. The problem is you will never be able to explain how this model works. because this model becomes so complex, you will never be able to explain how it works. This function will become very complex and it's very difficult to explain to a layman. So the idea here is, okay, we cannot do a global explanation like we did for the this approximate model, but then can we come up with some approximate explanation? So for the local data, so within this age, maybe this model works in a linear fashion, right? So you can come up with some local explanations. So essentially, what this example shows you is that there is a trade-off between complexity and explainability. So if you make the model very complex, which is here, right? If you make it complexity equal to 1, then it's very difficult to provide any explainability. But then this complex model might be the most accurate one. On the other hand, if you try to make it very explainable, so if you want explainability closer to 1, then you have to reduce the complexity somehow. And by reducing the complexity, in most cases, you're also reducing the accuracy. So how do you manage this trade-off between complexity and explainability is one of the key challenges in this area. Okay, so another topic which I'm working on is basically what is called a secure collaborative AI. So here the idea is very simple. In today's world, different kinds of organizations have access to local data. For example, banks might have access to transactions of their own customers, but they might not have access to transactions of other banks' customers. But then when they want to build a fraud detection model using this data, they have to do some kind of cooperation or collaboration in order to build a better model. So otherwise, they will never be able to detect certain kinds of fraud. Similarly, if you have a supply chain, basically you need to know what is happening at the other end of the supply chain. So let's say I'm a retailer, so I'm selling bread and noodles. The data which is available at the retailer, so how many units of bread or how many units of noodles are getting stored, is actually very important for a wheat supplier who has to kind of predict what will be the demand for this raw material, right? But then this kind of supplier who is higher up in the chain will never get to know the retail information. So that's why you have a lot of problems in the supply chain. You have overproduction, underproduction, and so on. So how do you basically handle this issue is one of the key things which we are trying to work on. So here the problem is data required to build this machine learning model is split across multiple entities. So it can be a horizontal split or a vertical split. By horizontal split, we mean similar in the case of banks, right, or hospitals. You have bank X will have some subset of customers, bank Y will have a different subset of customers, bank Z will have a different set of customers. So that is one kind of partition. But then once you have a customer, you have all the data about the customer. The particular bank has all the data about the customer. The second kind of partition is when you have this kind of vertical split, which means, okay, I want to predict something, but some attributes are available with me, some other attributes are available with a different party. So that's how vertical partition happens. And in this case, what we want is a fully decentralized model. So you can always come up with some local models which will work only based on your data. The problem is they will not be very accurate. The other end of the spectrum is a centralized model where you send all the data to a single entity, and then that entity does some learning for you, which is the predominantly used model currently. But then the problem with that approach is you are actually losing your data. You're giving your access to your data to somebody else. So this compromises privacy, and in many business scenarios, it compromises the competitiveness and so on. So what we really want is a decentralized model where you have your own data, you don't share it with anybody else, but still you are able to exchange some information with other parties in order to build a better model. So how to do it is one of the key challenges. And towards this, we kind of proposed a method for fair and privacy preserving decentralized learning. So here, the idea is, so there are two issues here, right? One is two issues with the sharing. So one is you don't want to lose access to your data, which is the privacy preserving part. The second problem is how do you ensure fairness in this case? So let's say bank X will have 1 million customers and bank Y will have only 100 customers. So if you try to build a model using only bank X data, then you can get, let's say, 95% accuracy. And then if you build the model using only bank Y data, you get only 50% accuracy. So now when these two parties collaborate and you get, let's say, a slightly better model, 92% accurate model. But then we know that bank X has contributed to this model more than bank Y. So you have to somehow come up with a fair reward. So either you have to say, okay, if bank Y has to get this more accurate model, then it has to kind of pay more money, or you have to basically give some kind of a degraded model. So bank X will get this better model, which is slightly better accuracy than its own model. Bank Y will also get a better model, but not the same one as bank X. Right? So how do you reward these different parties in a different way, so that they contribute? You get the rewards is proportional to the contribution. So that is one of the key problems which we try to address. So that's what we call as fairness here. So if you don't have much data, if you're contributing less, then you should not be able to reap the same rewards as the person who is contributing more. So how do you do that is what is addressed in this paper. Okay, so next I'll move on to this topic of machine learning on encrypted data. So here the idea is, in today's world, you have people who have data, you have people who have the computing resources, let's say the Googles and the Amazons of the world, or even the NVIDIAs of the world, where they hold all the computing resources. And then you have some data scientists who can come up with models that can work on your data. So how do you bring all these entities together? So that's where this concept of machine learning as a service comes in, right? So you kind of provide your data to somebody else who has the expertise to come up with a model, machine learning model, and also the computing resources to run the computations and give you the trained model on this data. So instead, if you try to build it using your own system, own expertise, you might not. You need to hire so many data scientists and machine learning engineers to build your own models. But you can do it in this kind of decentralized fashion, where you can send it to somebody else. They can, without compromising on your privacy and sensitivity and so on, and then the others can build the models. And to do that, the only way is basically encrypt your data, send it to somebody else, and then they train the model on the encrypted data and give you back the result. Okay, so basically, the goal is, can we do this end-to-end machine learning, which includes both training and inferencing over encrypted data in a completely non-interactive fashion? So it's not like, okay, there are ways to do it if you can continue to interact with the server, right? So you do some operations on the data, give it to the server does some operations on the data, send some intermediate data back to you. Again, you do some processing, send it back to the server, and then by a lot of these information exchange, you can learn the model. But we don't want that kind of thing. So what I want to do is, I just want to encrypt my data, put it on some server, the server learns the model and gives me back the result. So that is what we call as non-interactive. And to do that, we basically need to understand some core concepts in deep learning or machine learning. So in most of these cases, you have some training data, which is given by X, and Y is the label corresponding to the data. And you basically define a decision function or some objective function, which does the mapping from X to Y. And there is usually a loss function, which measures how well you are doing the mapping. So Y hat is the predicted value, and Y is the original label. So you measure the difference between these two, which is called as a loss function. And then the overall goal is to find the parameters of this model, theta, which minimizes the loss between the predicted values and the expected values. Right? And the way you do it is known as stochastic gradient descent. So essentially, these kind of functions are, you cannot solve them analytically. So what you do is you take some empirical approach, you take some compute some gradient of this function, and then take small steps opposite to the gradient in order to get the optimal values of the parameters. So this is how a general machine learning system works. So there are two key problems with this approach, right? So one is this function can be very complex, this minimization problem, right? So there might be a lot of local minima and that you can get stuck, right? Ideally, you want to get the global minimum of this function, but you can get stuck in the local minima. And the second issue is basically you have to do this iteratively over many steps. So you have a lot of sequential computations. So for example, if you have a simple neural network model, so here I just have one linear layer followed by an activation function, which is a non-linear layer, and say basically do the same thing again with one more linear layer and an activation layer, and then you compute the loss. So what you see here is basically one problem is you have to do the computation sequentially because of the gradient descent approach which you are following. The second problem is people have found that the deeper this network, so the number of layers you add in this network, it becomes more and more accurate. The expressive power of those overall system improves as you add more and more hidden layers into the system. And each of these hidden layers also have some linear computations and some non-linear computations. Right, so basically it's a sequence of computations. So from the input to the loss and then back, right? So when you train the system, you need to back propagate these loss. So you have to go forward and back many times within the same process. So this kind of model training requires a lot of sequential computations, which becomes a problem if you want to do encrypted training. So there are other kinds of activation functions. So I just showed you one example, which is sigmoid activation, but there are others like tanh, value, and so on. Okay, so now I introduce this concept of homomorphic encryption. So the key idea here is, okay, I have some data. Can I let others to do some processing on this data without they actually seeing what my data is? So this is similar to this example where what we call as Alice 12 store. So the idea is Alice has some raw materials, which is our data in this case. She does not have the capability to make a jewel out of this raw material. She needs to bring in some workers, but then she does not want the workers to see the data because they can steal it, right? So can I let the workers to process these raw materials and then build the jewel without actually giving the raw materials to the worker, right? So this is the analogy which we are trying to show here. And there is a way to do it, which is called as homomorphic encryption in the cryptographic domain. So the idea is somewhat similar to Alice putting the materials inside a locked box, and then she provides a glove to this box. So imagine there's a box which is locked and it has raw materials inside. And you cannot open the box, but there is a glove. So you can put your hand inside the glove and then do this processing, assemble the jewelry inside the box without actually seeing it. And once you're done, you basically take your hand out and then Alice can unlock this box and get the result. So this is very similar to what is happening in the encryption domain. So that is why it's called as homomorphic encryption. Okay, so it's a simple example. So let's say I have two numbers, x1, x2. If I multiply them, I get the value y, right? So now I want to encrypt these numbers, encryption of x1, encryption of x2, which are called as C1 and C2, or ciphertext. So what this unencrypted numbers are called plain text, and the encrypted numbers are called ciphertext. So if I give you this ciphertext, can I do some operation on this ciphertext and get some result, which when decrypted will give me the actual result? So here, let's say I want y equals x1 times x2, some product. This is the operation which I want. So can I do some other operation on the ciphertext, which will give me an encrypted value, which when decrypted gives me the actual result which I want? Well, this is basically homomorphic encryption. So there are some simple examples. So let's say a simple Rse crypto system. So this is one of the basic crypto systems used in many applications. So what they do is essentially take the input x1 and then raise it to some power e. And that's the encryption process. Similarly, if you give another data, they also raise it to the power same power e. So essentially, if you multiply these two ciphertexts, so this x1 power e is the ciphertext c1, x2 power e is the ciphertext c2. So if I multiply these two ciphertexts, I get x1 times x2 power e. And so what really happens is when you want to decrypt, there is an algorithm to do the decryption. So whenever you do the decryption, you get the result, which is x1 times x2. So this means that this Rse crypto system is homomorphic with respect to multiplication operations. So you can usually do multiplications given the encrypted values. Similarly, there is another system called as a Goldwasser-Mikali system, which does the same thing for an exclusive OR operation. If you have bits, you can encode one bit, encode the other bit, and then if you multiply these two bits, you get the exclusive OR of the two bits. So this is another example of a homomorphic encryption system. But what we really want is fully homomorphic system. So this RSA and GM crypto systems, they work for one specific operation. RSA works only for multiplication, whereas the GM thing works only for bits that do for exclusive OR operation. So can I come up with an encryption scheme which can do this same kind of manipulation, but it allows me to compute any kind of function. So that is why it's called fully homomorphic. So the idea is you give an encrypted, given this message M, you encrypt it using this algorithm ENC. You get a ciphertext. Basically, you also provide an eval function which gives you, it can take in several ciphertexts and the function f which you want to compute, and then computes the output of this function would be another ciphertext which, when decrypted, will give you the evaluation of this function at all these points m1, m2 up to mt. So if you can do this for any function, then it's called as fully homomorphic. So in 2009, IBM, one of the scientists at IBM came up with this first approach for fully homomorphic encryption. So it's still not fully homomorphic in the sense that you cannot do any computation, but you can do things like addition and multiplication, which means once you do both addition and multiplication, I can compute any low degree polynomial. So let's say I want to compute x cubed plus x squared plus 1, right? I can do this kind of polynomial computations in the encrypted domain. And I can do this somewhat efficiently. So that's one of the major breakthroughs that happened 10 years back. So I will skip the construction of the FHE due to lack of time. So this one basically, but I would like to stress only one aspect of it. So the problem here is the scheme which the scientists, the cryptographers came up with, basically relies on adding some kind of noise. So when you are doing this encryption operation, every time you doing an encryption operation or you're doing something to the ciphertext, you are adding noise to the ciphertext. And the idea is this noise has to be below some particular limit. Once it exceeds a threshold, you will no longer be able to decrypt. Okay. So this is how it works. I can share the slides with you later. But the basic idea is you can do addition and multiplication using this approach. But every time you do some operation, you're adding noise. And especially if you're doing a multiplication, then you're adding more noise because the noise gets multiplied. Right? So the problem is once the noise exceeds some threshold, the decryption will fail. So this basically limits the depth of the operations. So you can do only a fixed number of multiplication operations, especially additions. Usually you can do much more, but multiplication you can do, let's say, only few tens of multiplication. So you cannot take the same data, keep multiplying infinitely. You can do only 5 or 10 times. Before that, the noise will reach the threshold. So after that, you cannot decrypt. So this basically limits the depth of the operation. There's one more scheme called as the Ckk scheme. So the previous one which I mentioned works for integers or like binary representation. This one you can directly work with floating point numbers, but the idea is very similar. So each time you do an operation, you're adding noise, and once the noise exceeds the threshold, you cannot decode. And another issue with this floating point approach is the multiplications are not exact. So essentially, you lose a few bits of precision all the time. So on the left-hand side, I show the exact multiplication of a few numbers. Basically, you're trying to restrict the number of decimal points. So as you keep on doing multiplications, your results will get more and more approximate. And you lose more and more least significant bits. And this causes a problem in machine learning. So remember I talked about this deep learning function where you want to minimize this objective function. So essentially, if the objective function is very smooth, then if you try to minimize, you can go always, if you follow the gradient descent approach, you can go and reach the global minimum. If your computations are noisy, so if you're losing precision, then the same objective function will become something like this on the left, bottom left, right? It becomes a little bit noisy. So if you're trying to do this gradient descent and trying to reach the global minimum, you might still be able to do it with a little bit of noise. But when the noise again becomes higher, then you will no longer be able to reach the global minimum. You get stuck in some local minimum, which you don't want to happen. So another concept is what is known as a bootstrapping or recryption. So here the idea is, as I mentioned, you can do only limited number of multiplications. There's a depth to this depth limit to the number of operations. Clearly, you cannot do anything with 10 multiplications, right? So if you have a deep neural network with many hundreds of layers, you cannot achieve anything by having only 10 multiplications. So you need to have some way of increasing the depth. And one of the ways of doing it is what is known as bootstrapping or recryption. So here the idea is, so to decrypt, you need to have a secret key. So you use some hint about the secret key to the server, and then using that hint, the server will not be able to fully decrypt your value, but it might be able to do some processing so that it can reduce the noise which is being added, and it can continue to do some more operations. And then, but the problem is this is very computationally expensive. So each bootstrapping operation will take, in the order of seconds or minutes. So if you can imagine, if you are doing large number of computations, this will take a long time to do. So the idea here is basically the process ciphertext will have less noise. And by doing this repeatedly, you can improve your available depth, which means you can do more computations. But then the problem is it's very expensive. Right, so now we see there's a basic issue here, right? So one is you have seen the machine learning algorithms, which essentially thrives on sequential computations. The deeper the network is, it works better. And the more training you do, the more number of iterations you do, it works better. And it also has nonlinear activation. But then on the encrypted domain side, you can do only additions and multiplications. So you cannot do any things like exponential operations. So you need to kind of approximate this function somehow. Exponential or even a simple a ReLU function, right? It can be done very easily in the plain text domain. You can just compute max of 0 and that number that gives you the ReLU function. But then if you're trying to do it in the same encrypted domain, it's a very challenging problem because you cannot compute the max of 2 numbers. So there is a big challenge here how to do this thing. So that's why if you want to do a large real world problem, which we call here as ImageNet order of learning problem, which is typically what is useful in the real world, then you need to have you should be able to handle the number of sequential operations should be in the order of millions, and you want very good precision in the order of 10 power minus 3, minus 4, and so on. And these things have large number of parameters in the order of tens of millions or hundreds of millions. But then what you can do with today's fully homomorphic encryption is only this much. So there is a barrier today, which means you can do only up to, even with all this bootstrapping stuff, you want to run something in like a few days, then you can do only hundreds of operations, and the precision is also low. So how do you kind of bring these two things together is one of the key challenges. So what people have tried is they have tried to do inferencing. So instead of learning the training, learning the model parameters during the training process, you can do just the inference process. So once you learn the model on plain text data, and then when you want to do the inference, especially in the machine learning as a service scenario, you just send the encrypted data to the server. The server applies the learned model on this data and gives you back the result. So that kind of thing is possible today. But real training, people have shown only for some very simple kind of models like logistic regression and like a neural network with one or two layers. So that is the maximum you can do today. And to overcome this challenge, you basically need to come up with new ways of reducing the precision requirement. You need to come up with new networks like deep networks, which are not so deep, but it still give you the same accuracy. You need to come up with more efficient training algorithms, which does not require you to do this lot of iterations. And you also need to improve your homomorphic encryption scheme. So those are the directions in which we are working at the moment. So this, I'll just show you some brief results about the state of the art. So there are many big companies like Microsoft and IBM and MIT. These people are all working on this issue. They have come up with some solutions. Right, so they have shown that for simple data sets like the MNIST, which is a digit classification problem, you can achieve, you can do encrypted inference. Basically, here you're not doing the model training. Here you're just doing inference. Learn the model using plain text data, and then you're doing the inference on the say encrypted data. So that you can do with very high accuracy and also reasonably good throughput. So the MIT approach is kind of trying to do this in interactive fashion, but reduce the number of interactions. As I mentioned before, you do some processing, send some data back to the client. Client does some other operations, and then by do this interaction, you can do things faster and more accurately. But then the problem is you need to exchange a lot of data, which consumes a lot of bandwidth. And one of the key tricks which these people use is approximations for these different nonlinear functions. So let's say if I give a max function, how do I approximate it in, like, say, some kind of polynomial form? Similarly, if I do a sigmoid or a value function, how do I come up with some low degree polynomial which approximate this function well? So that is one of the challenging areas which people are working on. As I mentioned, some people have tried to do training, but mostly on very simple models like logistic regression. So one of our papers, which was published in CAPR 2019, where we tried to do a simple neural network, training for simple neural network. What we try to do is minimize the size of the computations. So essentially, if you know about this MNIST data set, you have these 28 by 28 images. So what we try to do is kind of make them smaller somehow, because 28 by 28 is like 784 dimensions. So then it requires a lot of computation. So we try to reduce it to 64 pixels, right? By cutting out regions of the boundary and then quantizing them and so on. So we try to reduce the number of pixels. Right, and then even with all these kind of magic, say training this simple 3-layer perceptron, just only 3 different layers for 60 samples, we put 40 minutes, and that will with all this parallelization, because each of these things, right? Let's say even though we have only 3 layers, after each layer there is a nonlinear activation, which takes some time to compute. And then you have to do some bootstrapping operation, which I mentioned earlier. So all this makes it consume a lot of time. So if you want to train a full model with many batches of data, it will take probably months or years at this rate. Yeah, but the good thing which we showed is it's possible to do some kind of, reduce it to some level, but at least, see, initially when we started off with the full model with the 28 by 28 pixels and this 3-layer network with all this number of hidden nodes, right? It took like 1.5 days to run one batch of computation. From that, somehow we are able to use some tricks to reduce it to 40 minutes. Which itself is a big thing, which itself is very high. It's not reasonable. So you need to be in the order of seconds in order to for it to be meaningful. Okay, so to summarize, so AI is far from being a solved problem, and most of the best AI minds are still focusing on the core AI issues, which is how do I improve the accuracy of my system. But then my main motivation, and there are many researchers who are working in this area, they think that, if you really want to deploy these AI systems in the real world, you need to pay attention to issues such as security, privacy, and trustworthiness. And a lot of these problems, one of the core challenges which keeps coming up is like, how do you manage the trade-off between complexity and explainability? So simpler models usually work much better. This thing has been known for a long time. So there's no Freeland's theorem and outcomes tracer, which were proposed in 1960s when the AI was in its very beginning, and they still hold true, right? So the simpler models usually work are better from the explainability point of view. If you want to do encrypted computations, from the adversarial attack point of view, all these things, simpler models are better. But then these simpler models are not as accurate as these complex models. So how do you manage this trade-off between complexity and explainability in machine learning, and which we are trying to address? So with this, I conclude my presentation. Thanks a lot for listening. And if you have any questions, I'll be happy to answer.
Hello, sir. It was a great session. There is one question by a participant, Meghna. She's asking, in the process of learning, is the data decrypted, or is it done on encrypted data itself?
It's fully done on encrypted data. So that is the beauty of the system, or the homomorphic operations. So you don't give the data any place. Only after all the computations are done, you give the final model.
Okay, thank you so much, sir.
May I ask one thing? Actually, it is my query.
Yeah.
Yes. Professor Karthik, thank you for a nice talk. Can you hear me?
Yeah, I can hear you.
Okay. It was really nice to hear from you. I have two queries. Actually, in your first problem, when you talked about the presentation attack, can you throw some light on the kind of features that you are using for handling the presentation attack?
Okay. So typically, let's say until a few years back, right, people are using what is known as this kind of texture features, which is things like local binary patterns and so on, because these things are not, you cannot recognize anything from the visual domain, but actually there are some minor patterns, texture patterns which appear in these images. If you are, when you're capturing a live image versus a fake image or a spoof image. So typically people are using these kind of texture features for the detection, which is like histogram gradients and local binary patterns and those kind of things. But nowadays, as deep learning algorithms have come up, everything is like they just pass the raw data to the deep neural network and then learn some model. So it's very difficult to say what kind of features are being learned by this model. So that is why it becomes important to do this generalization.
I have another query about the face recognition problem that you talked about, that in most of the commercialized face recognition problem, they deal with some kind of a typical face pattern like European, male, etc. And that may not be working properly when we take the African or something. So, and you said very rightly in your last answer that with the introduction of deep learning or convolution neural network, you never know which kind of actually feature will be effective for that kind of a problem. So in that line, my query over here is that in the era of deep learning and convolution neural network, people are possibly looking at coarser level feature to final level feature as on we pass on the level of the DNN or CNN. So in that case, the presence of eyes, lips, nose, etc., will be constitute the feature of a face. So will that be very much difficult to actually, or will we be requiring two different approaches for European male and say African male kind of a problem, or only one solution would be sufficient for both?
Okay. So the main idea which people are using is they understand that this is an issue because of the data imbalance and all these things. So they try to, when you're doing this deep neural network or a convolutional neural network, instead of just focusing on the accuracy, they try to introduce other kinds of penalization factors, right? So which says, okay, I want to improve my accuracy, but accuracy across these subclasses should be the difference in accuracy across these subclasses should be less. So they explicitly add that as a constraint in that optimization problem. So that's how they try to make it more fair for different sets of users. So they essentially the approach that they're trying to use is mark some sensitive labels. Okay, if I know age is a problem, ethnicity is a problem, gender is a problem, these are all sensitive variables. And when I'm doing the learning process, I try to penalize if there are variations across these sensitive labels. So that's how that is one of the main methods of addressing that problem. So if the system has 90% accuracy for one, so let's say for male and 60% accuracy for female, then that system will be penalized more. So it will be forced to learn something which is
okay. You are saying. I was wondering about the introduction of DNN CNN. Will that really matter for that one? Because DNN CNN is working mostly on the coarser level to final level features.
Yeah, so theoretically, a CNN is working from coarse to fine level, right? But actually, we really don't know what is the contribution of these different things, right? So ideally, the CNN, that's the intuitive concept is correct, but then we really don't know whether for this particular classification, whether this final level features are important or the coarser level features are important. So that's why by doing this penalization, you are forcing the thing to select those more coarse features. Right, so you want to have an eye, you want to have this kind of thing, and so on. So you need to have these coarse features for it to be classified correctly. So that's for that you need some additional kind of regularization or penalty.
Okay. Thank you very much. Thank you for your.
Yeah.
There is one more question from the participants.
Yeah.
Homomorphic encryption will increase the training cost a lot. Any comments on that?
Sorry, could you repeat the question?
Homomorphic encryption will increase the training cost a lot. Any
Yeah,
comments?
it will increase the training cost. That's what I'm emphasizing, right? So today, if you want to train a classifier for this digit recognition MNIST database, you can do it in seconds. Whereas, as I showed you earlier, if you do this on the encrypted domain, even when you follow parallel processing, it takes 40 minutes to run one single batch. So if you want to run the whole training, it will take months and not years. So that is why we are trying to come up with methods. I mean, we are trying to make changes in the cryptographic side also to make it run faster. At the same time, we want to reduce the number of computations in the machine learning side, so that training becomes feasible. Today, it's not at all feasible.
Neetaji, please unmute yourself. You are muted.
Okay, fine. So thank you very much, sir, for sharing knowledge of the possible attacks on the data, need of learning the encrypted data, and the various homomorphic encryption. Also, mentioning the state of the art for the encryption techniques. So definitely participants will use this knowledge in their research, those who are working in this domain. Thank you very much, sir, for being as well with us and sharing your knowledge. And
Yeah.
as a token
Thank
of
you.
love, yes, sir.
Thank you very much for inviting me. And if you have any questions, please feel free to reach out.
Sure, definitely, sir.
It was a nice presentation, actually.
Yeah, thank you very much.
You set the tone of the seminar series really good. Thank you for that.
Yeah, thank you. It's pleasure is mine.
Mita, would you like to present some digital?
Yeah, basically, I think Meeta has some network issues, so I am sharing. Just 1 minute.
Okay.
Yeah, so this is just a e-memento. Basically, the current scenario, we cannot give the physical types of memento at this time. That is just a e-memento from the IEEE SPS Gujarat section and the Nirvan Mani Institute and the IEEE Gujarat section.
Yeah, thank you very much.
So you will be mailing this to him, right?
Yeah, we are mailing after the event.
Okay, great.
Okay, thank you. Thanks a lot.
Yeah, and now I request to all participants, please open your video cameras so that we can take one screenshot. Yeah, just 1 minute. Just 1 minute. Okay, so thank you, Dr. Karthik.
Yeah, thank you very much.
Yeah. So our next talk will start from after the 10 minutes from the 5:30 p.m. and that talk will be by the Dr. Ashish Khare from University of Allahabad. He is already available here. And now I am handing over to the Dr. Bakul. So you handle the next session from the 5:30 p.m.
Okay, thank you. Thank you
You are
very much.
muted. Please unmute yourself. Yeah, thank you, Dr. Karthik.
Thank you.
Okay, see you guys after 10 minutes.
Yeah, so see you after 10 minutes. Suman sir, Dr. Ashish is here, so if you want to do some sit chat, so you can do it.
Okay.
Yeah.
So he's available, right?
Yes, he is available now.
Hello, Ashish ji.
Hello, sir. How are you?
Fine. I'm fine. How are you?
Fine. Really,
Okay.
it's nice to
Yes.
see you. I met you, I think 2.5 years back.
Right.
AICT campus.
Right, sir. I remember.
Yeah.
It's nice talking to you once again. Actually, this last 1 year, most of our habit has been changed.
Yeah.
So, you see, a couple of days back, one of my colleagues from Calcutta, he's right now in Kolkata. So he asked me, can you send me the office phone number of one secretary? So I told him that I forgot the extension of the secretary. I am not using it for last 1 year, so I forgot. I can tell you the first few digits of the general number, but not the last 3 digits of the extension. So that
Same
is
here
the
from
kind of
last 2 months. If we want to find any extension, we open the website.
right. So we forgot. It's a new normal kind of a thing.
This is the new normal kind of things, and ultimately in coming month, coming years,